Our next speaker is Dr. Dan Stanzione, who's the Associate Vice President for Research at the University of Texas at Austin and the Executive Director of the Texas Advanced Computing Center, TACC. Dan?
Thanks, Samir. I am here. Appreciate it. We do the ubiquitous slide sharing thing. All right. And you're seeing the correct screen, right? So
yes, we can.
Not the next slide screen. Okay. Thanks very much, Samir, Mike, and everyone for inviting me to talk today. And thanks to Hari for talking right before me. He's a longtime partner, and I appreciate all of his references to Frontera for scaling information in the talk. And that is one of the ways we work with the MPI community, is working closely with Hari on scale up and scale out of those things. We've had a very long, very productive partnership with DK and Hari and their team at Ohio State for many, many years. In fact, some of their students end up being on staff with us over time. So, but what I wanted to cover today is tell you a little bit about our stack today and just how we're doing stuff, particularly on Frontera and Stampede, and then how we'd like to see some of that evolve in the future, and a little bit about what the pain points are. And then we can talk about whatever, and I'll talk a little bit about where our connections are on the DOE ECP thing, which we have some of and would certainly like more. So I've given like 900 talks where I go through the specs and stuff for Frontera, and so that's boring and I'm not going to do it again. And if we had actually held this with the workshop for OpenMP this week, you would have been in Austin in this building at the meeting. So rather than do the ubiquitous spec slides, we'll do the 50-second data center tour. And the two machines I'm going to talk about the software stack on are Stampede 2 and Frontera there. Frontera is a bit heterogeneous in that there's a giant, more or less homogeneous CPU partition that you're seeing there with the 52U racks and the 6 megawatts worth of water-cooled servers there. It's a little over 8,000 nodes. But we also have some GPU subsystems. Yeah, 45 miles of InfiniBand cable. Stampede actually has 70, so it's the little one. There's all the flash storage associated with it, good mostly for blinking lights. And then there's the GPUs that are submerged in mineral oil for our sort of single precision workstation class GPUs. There's also a double precision substation subsystem. So the software stacks for those are a little bit separate. I'm mostly going to talk about on the CPU side what our software management sort of stack and practices. But that's more fun than a spec slide. And you know, had you come to Austin, this is what you would have seen, and this only takes 50 seconds. So that was a better way to see it all, I think. But since I am going to talk about Frontera, and I had to do the annual review 2 weeks ago, I have all the stats on the first year of production that I can share. You know, we've spent about 30% of the time since March on COVID things. Actually, there's a lot of DOE ties there. We run the Smiles for the Arvin's pipeline from Argonne that then moves over to do the deep learning part on Summit. But we've run about 1 million jobs, put about 50 million node hours out. Great uptime, great utilization, good on cybersecurity, few enough projects that we actually have a Slack community to talk to users, and we do that thousands of times. In the course of a year, the machine was number 5 when it came up. It's still number 8. We just got number 3 on the IO 500, and we did that using DAOS, which I know is of interest to many DOE folks at the moment, because it's the object store software of choice for Aurora. And we've done some commercial cloud integration and things like that that I'll talk about a little bit more lately. Because of that IO 500 and the work with Intel, and we actually did that benchmark using the 4th subsystem of Frontera, which is the Optane-based nodes. We have a small subset of nodes that are quad socket nodes with 24 Optane NVDIMMs. So they each have, I think they're the 256s. So we have 6 terabytes of RAM across each node of 16 nodes. We made a 100 terabyte file system out of Optane to do some of the DAOS testing. And we're actually currently working through Intel with a team at Los Alamos to test all the ECP software components that are IO dependent. So the HDF and NetCDF stuff, some of the MPIO and Audios type stuff on DOS using Frontera as the test bed right now. And we're both doing that initially on the Optane nodes, and then we're also setting up DOS on a portion of the more traditional SSD. Who knew we'd use the words traditional SSD file system? But the solid state part of the disk file system, where we have a bigger, petabyte scale file system with a few more connection nodes to go on. And I will say the only reason we're number 3 on the IO 500 is we were limited. We have a single HDR 100 rail into those Optane nodes. And so that limited our DOS performance to 100 gigabits per node. We actually had more available from the Optanes and from DOS. So Intel built an in-house cluster with 2 rails of network to it. They of course used OmniPath, but they put 200 gigabits in per node, and that's the machine that's number 1 on the IO 500 list. Was after they finished the Frontera testing, they're like, if we had more rails, we'd get number 1. Let's go do that. So I did not get them to give me the cards. It's a failing on my part. So. But we operate Frontera and Stampede, in the context of the NSF user space, and this does affect our software stack from. So just so everybody understands our context, Frontera is actually the easy one because we only have about 100 active projects on it at a time, and it's focused on some of the larger scale problems. As Hari mentioned, when he did his 4,000 node testing for EMBEDDING, we take about a week, a quarter to do just large scale runs on the machine. Which we've had about 12, we have sort of 30 big projects on the machine, and 12 of them have run in these sort of full system mode days at this point. 7 ran the first week of September, and they have to be able to run at least half scale to be, so 4,000 nodes or more, 220,000 cores in order to run in that time period. So we have mostly larger jobs and a relatively small number of users on Frontera. Stampede 2 is sort of our broad mission system. It's actually similar scale. It's about 6,000 nodes, but we have 2,000 projects active on it. And it has, so our data for the last 5 years show that there's about 35 or 40 binaries that get the top half of the cycles, and there's 4,000 binaries that get the other half of the cycle. So we get funded by NSF to acquire the systems and to operate and maintain them. But we actually don't get a whole lot in working with our users on their software, nor do we have really many levers to convince them to do good stuff with their software, because the science teams and their codes, all of our users are funded either by other parts of NSF, in some cases by DOE, or other agencies altogether. And we essentially operate as a user facility for these, and we're essentially competing with other user facilities. So being able to run their codes with minimal, they come in with fairly ridiculous ideas about how code should work, and part of our job is to make those fairly ridiculous ideas work, as well as doing the performance optimized stuff moving forward. And this is where I discover it's being recorded in panic. So, but nonetheless, we get very little time to work with, or funding anyway, to work with the code teams. And in the NSF space, there's no real roadmap for future systems. There's periodic, at least up until now, there's periodic competitions for systems, but funding's not announced. What the architecture is isn't announced until about 12 months before production. So spending 2 or 3 years getting ready for a new architecture is not something that happens. We're working on that, but that's the context we operate in now. So as I talk about our stack for a few minutes, please keep that in mind. So that's what we do. So, and I'm going to run through the stack. Some of the numbers for versions might be a little out of date because I stole some of these slides from various site visits, but Frontera and Stampede, the way the stacks work, are actually pretty similar and have a lot in common. We do CentOS based. All of our sort of install stuff is based on something that we developed in-house a long time ago called LOSF, which in turn uses Cobbler and RPMs to do just about everything. It is now distributed as part of OpenHPC. So we try and take the components we build, and at least if we're not stealing them from somebody else, we're trying to integrate them in OpenHPC. So they're at least out there. So, so if you get the OpenHPC, most of the tools we use are in there at some point. but it's CentOS based in addition to all the CentOS RPMs, because we've traditionally used RPM to do most everything. We have about 500 that we add. Again, not counting the GPU stack. And that's for things that are not downloadable, right? Either community code RPMs or something else. Those are ones we build in-house. And frankly, we do everything via RPM, right? If you want to do an overlay on the CentOS thing and configure a file on every compute node in Etsy, you know, you're going to write an RPM to modify that file. Is the way we push system changes and maintain consistency. And although we actually run many more with this, we sort of have two base compilers that we build most everything against, two MPI stacks that we build everything against. And so the libraries and community applications, you sort of multiply by the number of MPI stacks and compilers to get the number of things we have to actually build and install there. So just to fairly quickly run through what we have on the system, and again, we're on Intel 1819 now. Like I said, don't pay too much attention to these versions because the graphics old. But we run always the last several versions, maybe not the last several versions. We always skip the .0 versions of Intel compilers, but several versions of Intel compilers, as well as several versions of GNU compilers. And that covers most of our users. Our sort of LLVM builds we're starting to see more of, but are actually mostly people working with DOE components who are doing the LLVM stuff at the moment. And then of course we have the XL and NVIDIA compilers on the GPU side of the house. In fact, since we ran Wrangler, which was all AMD based, Intel's been our best performing compiler for the largest set of our users. But then there's a whole bunch of stuff that requires GCC. So we end up supporting both. And then on top of that, of course, we build our MPI libraries. And again, we work with Intel MPI and we work very closely with Hari's team. Again, we've managed to launch, and again, this is back to our users doing silly things on an 8,000 node machine with 56 core nodes. No one should ever launch 400,000 MPI tasks, but we still have some users in, say, I don't know, fluid dynamics who want to do one MPI task per core. So we have in fact launched jobs at above 400K tasks in both of those. As Hari mentioned, MVAPIC is the choice of many of our users because it launches so much faster than the Intel one, but we work with both of these groups to optimize our performance. And then of course we build all of our libraries on top of that, and it's the ones you expect for IO, for FFT, for solvers, and then we build the parallel libraries on top of those. So in the sort of centrally supported ones, and again, users build a lot more. So by the way, I'm not watching the chat, so if there are questions, feel free to interrupt at any time. But you know, we have the IO libraries, the FFT libraries, and the various solvers that we sort of centrally support from our team. And then community applications, and again, where users do build their own of these, we try and keep you know, correctly compiled and system maintained version of the big ones that we see in our workload. Like I said, there's about 35 that we can identify are the top 50% or so of cycles. So we have a standard LAMPS and a standard NAMD and a standard GROMACS, even though most people who run NAMD find Jim Phillips' home directory and run it out of there on every system that we've ever built in the last 10 years. But we have a fair amount of centrally built libraries that we maintain. And then all of our performance tools on top of that. And again, you just can't run a workflow of any kind without having the Python stuff out there now. So we're doing Python and our debuggers, DDT, visualization tools, plus some of our in-house performance tools like Exalt and, well, I think the system monitoring slide coming up on that. So we have the programming and the high throughput tools. We have our profiling tools, yeah, TACC stats, Tau, Exalt, our modules tool, LLTop, our Lustre performance tools, etc. All layer on top of that. And that's sort of our traditional HPC stack. And you know, there's no traditional HPC stack without also your data analysis and your machine learning stack as well. So we also build centrally supported versions of Caffe, Torch, and TensorFlow. But of course, those are almost hopeless to build. So we also have standard optimized containers, and users run less optimized versions of it all the time in there. And then upon that base, we still have users build. Most applications that run are sort of a user built A.out. there's a fair amount of, we wouldn't be supporting it if we didn't have a fair amount of use of most of those apps, but there's so many versions and customizations that's just sort of the build environment we give our users. We use LMOD as our module system, which is also an in-house tool, but used a lot of other places at this point. So to build, they build on top of that, and we try and make sure they build as optimally as possible on top of that. And then of course, everybody's stack now has virtualization as well. So we also do support containers on all the platforms now. Frankly, on Frontera in particular, they're not used where I thought they would be. But Singularity is the container system that we sort of guarantee support for everywhere. We've also started supporting Charlie Cloud. And we have a new one that we're supporting that runs not Docker, but Docker compatible containers, and will run the Kubernetes orchestrated workflows inside of Slurm. I forget what the workflow tool is called at the moment. So because we're starting to see demand for those sort of orchestrated services, and running Kubernetes on the big machines just doesn't really make sense for us directly, but running Kubernetes config files inside of Slurm seems to make some of those users happy. So, but we do support, direct checkout from repositories integrated with Slurm. You can download a container and run it. So as I suspect most everybody is, and obviously if you download a generic container not built right, it doesn't run as well on the system as something optimized. So we do build, like for the machine learning tools, performant containers, but people get others. The largest single container user by jobs, you would think it would be somebody doing machine learning or R-based data analysis or some of the things that we built containers for. Of course, it turns out that our largest container is a geoscientist, right, who just has a set of packages that are, Podman is the correct thing, Todd, yes, thank you. Yeah, we're starting to support Podman. It's run successfully experimentally. We haven't put it in the documentation yet. But we have a geoscientist who runs this thing called Underworld because he does subsurface work, and I think they probably think that's a pretty good pun. Admittedly, I couldn't do better. But it's nasty to build across platforms, so they've just started running containers wherever they go. And if we look at our Singularity jobs, it's the traditional sciences running traditional simulation that have actually become our largest container users. And some of that, sorry, wrong window. Some of that container mess I'm going to come back to in a moment, towards the end here. But so that is more or less the stack that users see when they log in at the command line. I will say we're starting to see people use it externally. So we have what I've started to dub Frontera-AS-A-SERVICE. We do support multiple APIs on the machine to allow you to submit jobs or move data files in and out without actually logging into the machine. So we support some in-house APIs like our TAPIS, which TAPIS, we're UT Longhorns, and TAPIS is a longhorn bull in Greek mythology, and it's also an acronym for TACC APIs. But it used to be our Agave APIs, are now known as TAPIS in the newest version, and that's used by a ton of the web gateways, our NSF CyVerse work, the Design Safe Natural Hazards work, our DARPA Synthetic Biology project. EKY is a run out of University of Hawaii, is a water modeling gateway. So we have about 30 that leverage TAPIS, but we also support other people's APIs, like Rob Gardner at Fermilab. His Slate CI toolset is sort of an overlay of services for OSG, which is where we run our Atlas and CMS stuff. And again, these are mostly built to do either web submission or automated workflows. And similarly, into our portals, we built connections to the commercial cloud for data publications to Azure, AWS, and GCP. So a couple of quick examples of that. So this is a slide I actually stole from Raw from the recent sort of high energy physics snowmass meeting, but it just shows from Frontera embedded in the Atlas and CMS automated workflows. And so they have, we gave them a virtual login node, actually a set of containers that they run the Slate services on and their MariaDB. And we give them some support for their file system so that they don't have to fetch all the data for every job, and it's pre-staged onto Scratch for some of what they do. And so they see Frontera as, a completely embedded resource. Most of their users don't have accounts. It's just an automated workflow. And then like the cloud integration, this is an example where it's used with some pretty big runs. So this is Ping Chang, leads a collaboration at Texas A&M, about 100 miles to my east, with some folks at INCAR and some folks in Taiwan at QNLM. And they are doing some of the UN high-res MIP simulations. So, you know, official climate change forecasts. It's running the CESM code, which is fun to build all by itself, but at 25-kilometer resolution globally. So they're big simulations, you know, not good cloud simulations, right? These are multi-thousand node, large-scale runs over large periods of time. But then they want to play with the data in this interactive analytics platform. So they use the, you know, they go to the portal and they push the data to Azure, and it's about 550 gigabytes for each simulation suite that they do. And they push it out there, and then they use another NSF supported open source thing called Pangeo that made these screenshots. But they share it with collaborators and they do all of their analytics in Azure, but the backend work is all done, is, you know, sort of traditional HPC that runs on Frontera. So they take use of that cloud platform. So we are starting to see more of these, you know, well, we see a lot more of these I don't build my own code type users who will just want to, you know, see, you know, essentially a set of services. You know, they wanted to use it like the cloud, even though they in fact need sort of HPC style resources. So, so that's what we do today. And with my last couple of minutes here, I want to talk about what we hope to do tomorrow. So, so at the moment, you know, Frontera is what it is. It's been pretty successful, but like all systems, by the time you finish deploying them, you're thinking about the next one. And so the NSF has started, has engaged us in doing this planning process for the next, what they're calling the leadership class computing facility. And I got to get that acronym changed, but the whole reason there's two C's, it's LCCF instead of LCF, is Argonne and Oak Ridge, who are the LCF. So we're staying separate from them with a leadership class facility, and it goes through the NSF, what's known as the MREFC, but it's essentially how they pay for things like Large Hadron Collider and LIGO and the telescope. So it has its own big, nasty project management and planning phase. But assuming all the planning goes well and Congress permitting, sometime in the FY24 budget, late 2023, we'd start construction of this facility and eventually build a production system to replace Frontera. But it's important that the funding mechanism is changing because it does give us that longer term planning horizon. So, so I recently finished our conceptual design plan for this, and it advocates for us to change our software strategy somewhat in a way that I hope allows us to partner better with ECP and other similar efforts around the world. And the big thing is that it actually acknowledges that there's some relationship between the machines you stand up and the software that runs on them, and the teams that have to run that software. So the plan is to have more direct engagement with research teams at the start of construction funding, so 2.5 years prior to system deployment. But after architecture selection and by connecting the funding to it, to create some stake for our end users in the performance and the success of the system, instead of saying, I don't run well on that architecture, I'll just switch to somebody else's machine. And we will not only have direct support for the applications, but for the libraries and tools that our selected acceptance problems depend on too. So we'll start to be able to do these sort of multi-year move the software things forward. And again, I hope that allows us to align better with ECP in the future. I will say though that what I see at the moment, particularly in places like Design Safe, where we're doing natural hazards work, or epidemiology, this was actually some of our COVID work, not all of our problems are exascale. And in fact, like all good tech requirements, there's an XKCD that explains what you really need. So I put on the appropriate XKCD comic, and this I think is just from like the last 2 months of XKCD. But you know, one of the things we had to start running was production epidemiology forecasts on Frontera when COVID broke out. And so, you know, we had a team, they wanted to work with us, they were super enthusiastic. When we actually got down into the nitty gritty of what they do, and none of you are going to be surprised like this, who work with these kinds of users, their workflow, shall we say, was like a dozen unconnected pieces of MATLAB code that you just ran each one of for each city you're interested in. And then there was a connecting model, and then you put all the files together and you hope for the best. And, you know, when you start doing COVID, you know, we did Austin models, but then you have to do the amount of interchange with Austin and any other city. And Texas has 254 counties, which is way too many, but that's another story. One has no COVID. It also is a county with 103 people of the 27 million that live in the state. But that aside, you know, you build a matrix of things that you're doing exchange between. And so you will go from cities to states to regions to country, and, you know, you end up with 1,000 by 1,000 matrices of these epidemiology runs. So, you know, first it was, well, 90% of the work is data cleaning for all of that. And then, you know, you take the MATLAB code and you slowly throw it out, and we rewrote an automated C++ code that actually does all this stuff. And Frontera actually does these runs every day. And then we have to do all the other parts of the workflow. We actually built their web portal for them. We explained to them why you don't go to the public with log plots, and we did all the visualization for them. And again, the data cleaning was the biggest task. But, and again, the comic is sort of the gap between, you know, what we'd like people to think, where we can come up with amazing frameworks for building code better and amazing algorithms for solving things better. But in practice, they want us to get pictures of their data into Excel. So, and this is what a lot of the real work looks like. So I'm concerned, and I would like to say this was courtesy of, but I never asked Torsten, I just stole the slide. So this is a slide Torsten Hoffler gave just in the last couple of weeks that I say is not credited to, but stolen shamelessly from. You know, when we talk about developing and maintaining large scale software, at this point, we barely know how to run it, right? Because as soon as we got containers, you know, it's sort of an excuse to not do good package management or dependency management. Arguably, it's a better way to do it. But the other thing is you just build whatever and put it in a container. So, so this is his containers are the end of software engineering as we know it. But so our biggest problems are probably not in extreme scalability, but not letting just the day-to-day management, and I know SPAC is involved, is a tool to help deal with this, but to not let things like dependency management make it so impossible to use that people just stitch together whatever cloud services are out there and live with it. So, and we end up irrelevant. So I think managing the complexity of the stack is as important as managing the scalability of the stack moving forward. And with that, I'll stop with a couple minutes left over for questions. So thanks very much. Oh, and thanks to our very big team that helps do this, including Ohio State and Hari and many vendors.
Sure, Dan.
So Mike's asking, what's the trend of native versus container? Hey, Mike, I think I saw you on the ASCAC call earlier this morning. So the trend is, so container runs are definitely growing, and they're growing in volume pretty quickly. They still are the smaller runs, right? So at this point, I bet if I counted jobs, it's like 15% of the jobs are containerized, but probably 2% of the cycles burned are containerized. Now that is up from like 0 2 years ago. So it's growing pretty fast. But it's no longer, it's far from the dominant mode around the large users. But like I said, you know, some of our longest term users, some of our National Academy level users do have their workflow containerized. So I'm a little bit surprised by who it is. And it's growing fast, but we've not done a 4K or 8K node run that is containerized, so they don't get the bulk of the cycles. And then Todd, yes, what do users do for dependency management? Most of the center effort is spent on RPM, which is true, and RPMs require root, which is not exclusively true, but mostly true. So, and yes, we don't ask users to do RPM. So we are trying to support SPAC for users. It tends to get them to each build their own version of Python or something. And so it's caused some fairly large expansion of our installed software base in some instances, and we try not to have them run from, the advantage of our central packages is we push them mostly to local storage on the nodes so that we're not generating, 80,000 metadata requests per second to the Lustre file system to do glibc requests and things like that. And so that is an issue we've struggled with SPAC along with some of the ones Hari mentioned, but for the most part, they're doing, there's still a fair amount of configure, make, install. We are trying to increasingly support SPAC for user level work. Yeah, sort of where we could target install is going to be an issue for us, but yeah, so that's the short answer, right? In many of those cases, if it's not something that a lot of people are using, we do personally, by personally, I mean my staff does. I never do this, but we have folks who will go and help people build things if it's sort of a one-off. Yeah, and so yes, picking up central installs automatically is something that'll be a huge help to us. And yeah, I have John Kaz. We sent some people to this forum in person last year, and we will continue to do so because that is something we intend to support definitely. And that new function will be a huge help, Todd.
Thank you very much, Dan. We look forward to engaging with your team and working together with E4S and SPAC.
All right, let me stop the share for the next speaker.